All right, if you're tackling AQA GCSE Physics, you know that questions about circuits are pretty much guaranteed to pop up on your exam. So in the next few minutes, we're going to absolutely master section 4.2.1. That's current, potential difference, and resistance. The goal? To make sure you can walk into that exam feeling confident and ready to nail it.
So here's our game plan. First, we're going to get to grips with what electric current actually is. Then, we'll dig into the one formula that kind of rules them all, Ohm's law. After that, we'll meet the rebels of the circuit world, the components that like to break the rules. And finally, we'll wrap it all up with a super focused revision checklist so you know exactly what you need to remember.
Okay, let's dive straight in with Section 1. We are going right back to basics, looking at the absolute foundation of every single circuit out there, electric current.
Now, before we get to the official definition, just think about this for a second. You flip a light switch, and the bulb comes on instantly, right? But what is really happening inside that tiny little wire to make that possible?
And there it is. That's the official AQA definition you'll want to have in your back pocket. At its simplest, current is just a flow of electrical charge. But, the most important word on this slide is rate. Current isn't just about charge moving, it's about how much charge is flowing past a point every single second.
And that idea of rate leads us directly to our first essential equation. It links charge, current, and time all together. Charge flow, which we call Q, is equal to the current, I, multiplied by the time, T. This one's a non-negotiable. You absolutely have to be able to recall it and use it.
Okay, now listen up, because this is where so many students lose easy marks. The units. For this equation to work, your charge, Q, has to be in coulombs, your current, I, in amps, and your time, T, must be in seconds. It's a classic exam trap to give you the time in minutes. Your very first step should always be to convert it into seconds. Don't get caught out.
All right, let's move on to the big one, Ohm's law. Honestly, the best way to get your head around how current, voltage, and resistance all work together is to just imagine electricity as water flowing through a pipe.
So for water to flow, you need some kind of pressure, right? Like from a pump? Well, in a circuit, that push is what we call potential difference, or you've probably heard it called voltage. It's the driving force from the battery or power supply that gets the electrical charge moving. It's as simple as that. No push, no flow.
And then you've got the flow itself. In our water pipe analogy, that's how much water is flowing past a point each second. And in a circuit, well, that's the current, the rate of flow of that charge we were just talking about.
And finally, something's got to get in the way. In a pipe, maybe there's a narrow section that restricts the water flow. In a circuit, we call this resistance. It's anything that opposes the current and just makes it a bit harder for that charge to get through.
And here is where it all comes together. This is Ohm's law, and it is probably the most important equation in this entire topic. Potential difference, V, equals current, I, times resistance, R. You need to know this one forwards, backwards, inside out. It is the key to solving most of the circuit problems they can throw at you. So what does this actually mean in practice? Well, if you keep the voltage the same, the relationship is really simple. As you can see here, if you have high resistance, so a really narrow pipe, you're only going to get a small current. But if you have a low resistance, a wide open pipe, you'll get a really large current. They have an inverse relationship.
And now for the really interesting part. You see, Ohm's law is fantastic, but it works on the assumption that resistance is this constant, fixed value. But in the real world, some of the most useful components are the ones that actually break this rule.
So first, let's look at a component that follows the rules perfectly. We call it an ohmic conductor. As long as you keep its temperature steady, its resistance stays constant. This means it obeys Ohm's law exactly. If you double the voltage, you get exactly double the current. It's perfectly proportional.
And this is what its current voltage graph, or IV graph, looks like. It's a perfectly straight line that goes right through the origin. This graph is the visual signature of an ohmic conductor. You see this, you know straight away, the resistance isn't changing.
But now, have a look at a filament lamp, like in an old light bulb. The graph curves. So why does it do that? Well, as current flows through that tiny metal filament, it gets incredibly hot. This makes the metal ions inside the wire vibrate like crazy, which makes it much harder for the electrons to pass through. So as the temperature goes up, the resistance goes up too. And that makes it a non-ohmic conductor.
Okay, this table here is pure gold for your revision. You need to know these four components like the back of your hand. We've just done the filament lamp, then you've got the diode, which is basically a one-way street for current, and then the two special sensors. the thermistor, where resistance actually decreases as it gets hotter, and the LDR, where resistance decreases as it gets brighter.
And why do we even care about these rule breakers? Well, because they are incredibly useful. A thermistor's changing resistance is exactly what you need for a thermostat that controls a heater. And an LDR's sensitivity to light? Perfect for making streetlights turn on automatically when it gets dark.
Right. We have been through a lot of key concepts there. So now let's just boil it all down to a simple, powerful revision checklist. If you know these things, trust me, you are in a fantastic position for your exam.
Here it is, your 4-step plan. Number 1, know your circuit symbols. Number 2, know those 2 key equations, Q equals IT and V equals IR, inside out. 3, be able to draw and explain the IV graphs for the resistor, the lamp, and the diode. And 4, be able to describe how resistance changes for those 4 special components we just looked at. Master these 4 points, and you've pretty much mastered this topic.
And to finish up, here's a final thought for you. We know LDRs are in streetlights, but I can almost guarantee there's one in the device you're watching this on right now. So, using what we've just covered, how does that light-dependent resistor tell your phone screen to get brighter or dimmer? It's physics, right there in your pocket. Have a think about it, and good luck with your revision.